it for the roll, and let's get this show underway. Got a bit more reliable internet connection today, so we should be having less lag on stuff. So let's get the OneNote up, and the interface looks a bit different as well. So here we go, starting the lesson in OneNote. Here we go. All right. So today, as I said before, we're going to look at exercise 9.1, which is to do with the gradient function, and 9.2, which is to do with area under a curve. And today, it's going to be a little bit easier, I think, than what we covered last week. Chapter 8, towards the end, was a little bit tricky. So especially 8.3 with those transformations. Okay, so here is what we're looking at today. The gradient function is, I've just got a little chart over here to kind of help us explain what's going on as well. So if we have our original function f of x, and we know how to do the derivative, so which is f dash of x, and then the second derivative would be f double dash of x, or f double prime, as they say in America. The derivative is if we were going downwards following this arrow. Now, if we started with the gradient function, which is the one that I've highlighted in green, and we want to work out what the original function is, it makes sense to do the antiderivative, which is the opposite of differentiation. Okay, so to find out what the original function is, f of x, all we do is we take the antiderivative of the gradient function, which is this thing here. That's essentially all 9.1 is. So we're going to do a couple of examples. So the first one is where we're going to find the equation of the curve if the gradient function is this. So they give us the derivative function, or the gradient function, and they also give us the coordinate that this function goes through. And this is a clue to help us work out what the constant value is, because whenever you antidifferentiate, you get a constant value. And so we want to work out what that C value is. So the first step here is we want to antidifferentiate this thing, just like that. And then use the coordinate, use the fact that it goes through 0 and 1. So 0 is the x value, 1 is the y value. And then use those bits of information to substitute into your antiderivative to find C. And if you wanted to pause this video right now, you want to try this for yourself, please try and do that. Otherwise, we will keep going. So let's look at the antiderivative of this derivative function. So when we antidifferentiate anything with square roots, you just have to remember it's easier to represent this using fraction powers. So that's where it's the antiderivative of x plus 1 in brackets to the power of a half. And then what we're going to do is just apply the rule. So we could, if we wanted to, do the reverse chain rule, which is the derivative of x goes out the front in here, and then we have a k value. But because this is just a linear function, it's actually just as straightforward as adding 1 to the power and dividing by the new power. And because the coefficient of x is just 1, we don't have to worry about any k values or anything like that. We can just apply the very first integral rule, which is add 1 to the power, divide by the new power. So let's just tidy things up a little bit now. So when we divide by 3/2, it's essentially the same as multiplying by its reciprocal. So you flip that upside down and make it 2/3 out the front. And now we're going to use this information. We're going to use the coordinate that we got given to us in the question. We're going to substitute the x value, which is 0, in for x, and the y value, which is 1. And so when we do that, when we substitute in there, we're going to have all the information we need to solve for the constant. And when we do that, the bit inside the brackets is convenient because that's just going to be 1 to the power of any power, no matter if it's a fraction power or anything, it's just still going to be 1. 2/3 of 1 is still going to be quite simple to work out, so 2/3. And all of this has to equal 1 because that's the y value in the coordinate. So therefore, when we solve this equation, we get C equals to 1/3. So when you're answering these questions, it's really important not to just stop at this point, but to actually say what that original function is. So you need to say y equals and write it all out like that. So 2/3 of x plus 1 to the power 3/2 plus 1/3. And if you wanted to write it in terms of what the original question says, then it's just a case of using our index laws in the right ways with the right square roots and powers. So this one here turns into 2/3, and it's the square root of x plus 1 to the power 3, because we've got the power 3 up the top here. And because we're adding a third on the end here, we might as well just have it all over the one fraction. So it's plus the 1/3 bit there. Okay, so if you've got any questions today, what I might get you to do is if you can write them down somewhere, maybe in a piece of paper or something like that, so you can remember the questions, and then when we go over to Microsoft Teams after the lesson, then you'll be able to remember which questions you had. Okay, question 2, which is question 6 from exercise 9.1. This is our second example. It says the tangent to the curve y equals f of x at the point 0, -1 has the equation y equals 2x minus 1. The gradient function of the curve is given by this. dy dx equals ae to the power x plus b. Find the equation of the curve given that it also passes through the point 1, 0. So there's a bit going on in this question, and these are the types of questions you're going to see in tests and exams, because there's a few clues that are given to you at the beginning, and you're going to have to sift through those clues to come up with some equations, some different equations, and then solve them simultaneously. Okay, so that's what I've written down here as the steps. So step 1 says use the clues in the question to come up with some different equations. Sometimes there'll be 2 equations to solve simultaneously. Sometimes there'll be 3 equations to solve. Sometimes it's a bit easier than that, and you can pretty much get the answer just by eyeballing the bits of information in the question. But this one, we're going to come up with some simultaneous equations. So the first clue is the tangent line. This one here, y equals 2x minus 1. So we've got our function, and this tangent line is a straight line that just touches our curve at 0, -1 at one spot, and it has a gradient of 2, because we know that because the gradient of the tangent line is also 2. So that's our first clue. We're going to have to come up with an equation from that clue. The second clue is to do with how the original equation goes through 2 coordinates. It has this coordinate here where the tangent equation hits it, and it also passes through this coordinate here, 1, 0. So that's the 2 clues we have for this question. We also get given that the gradient function has this as its starting point, so we're going to use that to help us with clue number 2. So what I want you to try and do is, same as last time, we're going to pause the video, and if you want to have a go at this question yourself, recommend that you have a go at it. I've got here step 2, added bonus, try and calculate the exact values of the coefficients of f of x. So if you've done this question already and you've got the answer using the calculator, have a go at this question again, but try and do it by calculating the exact coefficient. So that means giving your answers in terms of fractions and in terms of e in this function. So as I said before, if you want to have a go at this question, pause the video now and have a go at coming up with the equations you're going to need from the 2 clues, and then solve for the variables a and b. And I'll give you one other clue. There'll actually be a third variable that you have to solve for. There'll be an a, a b, and also a c in there. Okay, so as I said, if you want to pause the video, do it right now and have a go at this question yourself. Otherwise, we're going to go through it. All right, so first clue is this one. The tangent line goes through 0, -1, and has a gradient of 2. What that means is that the derivative f dash of x has to equal 2 when x equals 0. The gradient function has to equal 2 when x equals 0, because the gradient of our tangent line is 2 at that point. So that's what we're going to do. We're going to use that information, and we're going to say, okay, well, the gradient function, that's that dy dx, has to equal 2 at x equals 0. So let's put that information in. So the gradient function is given to us in the question, that's dy dx. I've just changed it to f prime of x, or f dash of x, just so it's just a little easier to do this notation all the time. So then e to the power x plus b is given to us in the question, and all we're going to do is we're going to substitute x equals 0 into this clue and come up with an equation. So we're going to get e to the 0. E to the 0 is just going to be 1, plus b has to equal 2. So our equation is going to be this, a plus b equals 2. That's our first of our simultaneous equations that we're going to come up with for this question. So that was to do with clue number 1. Clue number 2 was to say that the equation of the curve, the original function, not the dy dx, but the original function, f of x, or y if you like, goes through these two coordinates. So what we're going to do is to get that original function, we're going to have to anti-differentiate this thing. So we're going to have to anti-differentiate f dash of x to get our original function. And when we do that, we're going to have a constant at the end of it as well. So we're going to have some a's and b's in our antiderivative, but we're also going to have a constant as well. So here is what the original function is. You're like, well, that's like just doing the antiderivative, which is exactly what it is. So here we go. If we take the antiderivative of the f dash of x, this bit here, because e to the x is such a simple function, and we know that the antiderivative of e to the x is just e to the x. There's no coefficient in front of the power there. So the antiderivative of e to the x would be as if you took the a out the front of the integral. You could do that for this if you were just taking the integral of this section alone. It's just going to be e to the x. So putting them together, it's a e to the x is the antiderivative of that bit there. Okay, so that makes it nice and easy. The antiderivative of b just becomes bx. And then when we take the antiderivative of all these things, we need to have a constant on the end. Okay, so plus c. Now we have an equation with three variables, 3 letters, a, b, and c that we want to solve for. So let's use the first coordinate clue that we are given to us, that this function goes through 0, -1. So when x equals 0, we're going to substitute -1 for y. So when f of 0, the y value is -1. So I'm going to put 0 into my equation for x and see what we get. Simplify it. So it's a times e to the 0. E to the 0 is just 1. B times 0 is just going to be 0. So that's going to be nice to cancel out. And then we have the plus c at the end. So we have -1 equals a plus c. That's our second equation that we want to solve simultaneously. The final coordinate clue is this one, that the original function goes through 1 and 0. So same process again, we're going to substitute the x value of 1, the y value of 0, and come up with a third equation. So this one's going to be a little bit more tricky because we're going to have nothing that kind of cancels each other out, but we're just going to get a e to the 1 plus b plus c has to equal 0. So now we have 3 equations. We're going to try and solve them simultaneously, and we're going to try and do it without a calculator, even though some people would be like going straight to the calculator now and doing it, which is fine if you're doing a calculator-based test, but we're going to try and do this without a calculator and get those exact values that I mentioned before. So the first one, I'm going to rearrange, I'm going to use the substitution method. So here are our 3 equations. I'm going to rearrange this first equation to get b by itself. Okay, so b equals 2 minus a. And I'm going to rearrange the second equation to get c by itself in terms of a. I'm going to get both of these in terms of a so that I can substitute it into the third equation and then solve for a that way. Makes sense. It's probably the easiest way to do it, the substitution method. So here's the third equation, and every single time I see a b, I'm going to replace it with 2 minus a, and every single time I see a c, I'm going to replace it with -1 minus a, just like that. And then it's a case of simplifying this bit and see what we get. So we get a e to the 1 plus 1 because we've got 2 plus the -1 is the 1 there. -a plus -a is minus 2a. And so now to solve this equation, you get the 1 and you put it onto the left-hand side and subtract 1 from both sides. And then you want to factorize out the a on the right-hand side. So when you factorize out the a on the right-hand side, it'll be a outside the brackets of, and then you've got e to the 1 when you divide this term by a, and you've got -2 when you divide this term by a. So here we go. A is just going to equal -1 divided by e to the 1 minus 2. That's the exact value for a. And then we substitute it back into here for b. B is going to equal 2 minus whatever a is. So it ends up being 2 plus, because the 2 negatives make a plus. 1 over e to the 1 minus 2. And then if we substitute a into this one here, we're going to get this case here, 1 over e to the 1 minus 2 minus 1. So I've just kind of, because of the double negative again, I've put that term out the front, and then made it minus 1. So they are the exact values of A, B, and C. But as decimals, if you wanted to work them out using decimals, you can either just type them in the calculator or use the solve function. This is what the decimals say. But to answer the question, let's put all the bits in. So the original function is going to be negative 1.39, which is this A value as a decimal, e to the x, plus 3.39x, which is the b value at the front, the b coefficient, minus 0.39. So these are all the coefficient values rounded to 2 decimal places, and that is what the original function is. Okay, so we're just going to be taking a pause for 30 seconds while I transfer over to the next exercise. So I'm just going to go to this slide. Just bear with me. And then we will start the next exercise. So as I said before, if you've got any questions regarding anything I talked about, if you just write them down, and then we will I'll try my best to answer them in the Microsoft Teams chat we're going to have in a moment. Okay, so let's just go back to live screen. I did it again. Keeps going to sector. All right, so exercise 9.2 deals with this idea. So area under a curve, and we've been working with this for a while now, but today we're going to be a little bit more specific in dealing with area rather than integrals. Okay, so in chapter 8 we're dealing with integration, and we were talking about the fact that when you take the integral of a function you can get these negative parts, which are the regions below the x-axis. So today we're looking at area. So when we're dealing with area, we shouldn't have any negative parts or negative areas. Okay, we'll have negative integrals, but we won't have any negative areas. So the area under the curve and above the x-axis can be calculated by the definite integral of the function. Okay, so that's what we've covered before. So you've got this random function, and the area underneath between a and b is equal to this thing. And this is using the fundamental theorem of calculus, the first one we talked about. But what if you want to calculate the area and part of the graph is below the x-axis? That's what we're going to be focusing on today. So some parts of the graph are trapped, but it's underneath the x-axis. How does that change things? All right, so this is the example I've got, and I'm just going to make there so you guys can see all that bit. So here's my cubic function. It's a negative cubic function, and we have part of the graph that goes below the x-axis, and quite a bit of the graph here, a big chunk of area, is above the x-axis. So when you're looking at these questions, it does help to get a bit of a picture of the type of function you're dealing with. So that's why I recommend doing a little sketch, a little bit of a plot, to kind of see what sections of the graph might be below the x-axis, and they're the bits we have to be careful with. So in this one here, here's my plot, and I've got the x-intercepts, because the x-intercepts are really pivotal to finding out the regions below the x-axis. So I've got -3, 0, and 5 are the roots of this function. And so what we're going to do is we're going to work out the integral of this function between -3 and 5. We want to work out the area trapped between -3 and 5, but rather than just doing it in one hit, we're going to split it up. We're going to work out the integral of this section first, which we know is going to get a negative value, and then we're just going to convert that to a positive number using absolute values. And then this bit, we're going to do the integral between 0 and 5 of our function, and that will calculate that. And because this bit is already above the x-axis, we're not going to have to do any adjustment to that. It's going to be fine. So here we go. So I'll just zoom out so you can see it all in one screen. So here we go. The area in this first red section, I've just labeled down here, is the definite integral between -3 and 0. I don't want to go any further than that because that's when the graph goes on the other side of the x-axis. And when I calculate that, I end up getting -4. I just made up this number because just make it for this particular example, because I'm not giving you what the original function is. It could be anything, but I'm just saying the integral of that section there is -4. So although the integral is negative, we say that the area for that section is actually the absolute value of -4. Remember, absolute value is just in essence how far away that number is from the origin on the number line. So if you think of the absolute value of -3, it's 3 units away, so that would be 3. So the absolute value of -4 is 4 units, or 4 square units, because we're dealing with area. Okay, so that's where the units come into play today as well. And the area of the green section here is the integral, the definite integral between 0 and 5 of our function. And so this one I just made up a number as well. I just said, okay, that looks like it could be around about 10 for this particular example. So the definite integral for that one would be 10. So the area would also be 10 because it's above the x-axis. We don't have to do any absolute values. But if you did, the absolute value of 10 is still 10. So that doesn't change. The total area is adding these two sections together, but not the integrals, we're adding the areas together. So the area of the first section is 4, and the area of the second section is 10. So 4 plus 10 gets us 14 square units. Okay? Hopefully that's fairly straightforward. But what if we didn't want to plot the graph or solve for the roots? Is there a quicker way? Is there another way? Say, for example, this could be in a calculator section of a test. Is there a better way than rather than to, graph the function, work out the roots, and then try and get to the area that way? And there is. There is a way to do it using the absolute value function inside the integral. And you can do this on your calculators. And I've got a bit of an example here. So with the first example that we've got just up here, the area between -3 and 5. So this same graph we're doing here between -3 and 5. I've just got two scenarios, and I'm asking the question, I'm posing the question, which one of these would give the correct area of the example above? And the other question I pose is, what's the difference? Would they give the same value? So what I will get you to do is just pause the video now and have a bit of a think about it, and think about which one of these would give the correct answer. And if you want to write it down, have a guess, either 1 or 2. And then we'll explain it. Let's look at scenario number 1 first. Option number 1, okay? Option number 1 says it's a bit like doing brackets. So this is kind of like, the absolute value is kind of like doing brackets. We have to do this bit inside the absolute value thing first. So this is just saying the definite integral between -5 of the function. And this one here, this will have negative numbers and the positive numbers. So what it's actually doing is it'll work out the -4 definite integral and add the 10 part to it, and we'll get a definite integral of 6 for the bit inside the brackets. Then when we apply the absolute value to the 6, what we're essentially doing is saying the absolute value of 6 is 6, but 6 is definitely not the area that we came up with in the question. So this one does not give you the absolute value of the right area. Like it doesn't calculate the area correctly for you. Let's have a look at this one and see what's going on in this particular scenario. So option number 2, and again I'm going to show you visually what this looks like. So if we were to plot the absolute value of f of x, this is what it does to the graph. It flips the graph, it reflects the graph. Let's get my face out the way. It reflects the graph, any part of the graph that's below the x-axis, it reflects it above the x-axis. And anything that's above the x-axis, it keeps it there. So it just basically reflects any part that's below the x-axis above it, and any part that's above it, the x-axis, it keeps it there, which is perfect for our scenario, because when we do the definite integral now of this function here, all the regions above the x-axis. So we can just go straight from -3 to 5, like this, from -3 to 5 of our absolute value function, and all the negative regions get converted to positive in this section and added together. And so it's essentially saying the absolute value of -4 plus the absolute value of 10 equals 14 for that particular thing. So it just does it simply and nicer. And option 2 is definitely the correct way. And in a test, if you've got a question like this in the calculator section or exam, definitely try using the absolute value function in your calculator and doing it so much quicker. It takes the thinking out of it. You don't have to worry about x-intercepts or anything like that. Okay? Next part, the next scenario, and this is the last thing we'll look at today, is what if you want to calculate the area trapped between the graph and the y-axis. We've been doing all our integration so far between the graph and the x-axis, but what if now we want to change things up and we want to look at the area trapped between our function and the y-axis? Is it possible? Yes, it is. So here is an example. This is one I've just made up as well. I've got a cubic graph here. So I've got a function y equals x cubed, I think it is. And I've plotted it here, and we want to work out the area trapped inside this region here. So I'm just going to zoom in so we can see a little bit clear what we're going in, and then I'll zoom in even further about what's going on here. So the way I'm going to think about this time is rather than, so just zoom out just a fraction, rather than thinking about it in terms of vertical rectangles, thinking about it in terms of horizontal rectangles, so rectangles that go this way. So what we're going to do is we're going to work out the area of each of these rectangles and do like an approximation method, exactly like how we did before, and then apply that to integration, okay? So let's zoom in a bit further in here and see what's going on. Okay, so this is the bit that we're interested in, okay? So here is the top part of our graph. This is the y-axis here, and here are our individual rectangles, and in green I've highlighted just one of these rectangles. I made it just a little bit thicker so we know what's going on, but essentially what we're going to do is look at what happens when we get these rectangles and have them thinner and thinner and thinner and add them all together. So let's look at the dimensions of this rectangle. Okay, so let's look at the width. The width in this instance is this section here. It's kind of like the height of my rectangle. And the height is delta y. It's the difference in my y values this time. It's not delta x because we're dealing with the vertical axis. It's delta y. That's the width of my rectangle. The length of the rectangle, or just before I get to the length, says remember we want to sum all the rectangles as this limit, as this delta y gets smaller and smaller and smaller, as close to 0 as we can. So we want to work out the sum of all the rectangles as the limit of delta y gets close to 0. That's when the integral comes into play. The length of the rectangle is the value of x this time in terms of y. So what that means is, if I go back to my original graph, because I've got the thing drawn on the x-axis, kind of doing things in reverse. So this is the y value over here on this y-axis, and what we're trying to work out is what the x value at that point in time is, okay, at that point on the graph is. And that is f of y. Just like all the values on this y-axis we call f of x, it's the function, it's the y value at the x coordinate. This is the x value at the y coordinate, okay, it's the x value at the y coordinate. So, with that in mind, we're going to rearrange the function this time to make x the subject to help us work out these areas. Okay, so we're going to rearrange the function and we're going to say x equals f of y. So in terms of our problem, we have the original graph as y equals x cubed. Y equals x cubed. And so we're going to have to rearrange that to work out the area of this trapped region. So we're basically going to do this. The area is going to be between -3 and 5, and notice I'm using the bounds on the y-axis as well. We're not using the bounds on the x-axis. We're going from -3 to 5 on the y-axis of our function f of y delta y. It's not f of x, it's f of y delta y. Okay, but does this integral actually represent the correct area? The other question I pose is, what about the region that's trapped on the left side of the y-axis? This bit on the top here, we have some part of the section on the right side of the y-axis and some part on the left side of the y-axis. How does that change things? And it's just like with the x-axis. We will have negative integrals with this stuff, and so it's important that we understand how it all works. Okay, so I've drawn it again. Here's our scenario. The bit that's to the right of our graph, of our y-axis, that's the positive side. That's the positive side. And the bit that's to the left of the y-axis, that's the negative side when we're dealing with integrals with the y-axis. Okay? So what we're going to do is, if we do the definite integral sections, and if we have some part of the graph that's to the left of the y-axis, we're going to do that absolute value trick again, and we're going to convert those negative integrals to positive areas. Okay, so here we go. This is our original function, y equals x cubed. Y equals x cubed is my graph here, that purple line there. First thing you're going to do for these type of problems is you're going to rearrange to make x the subject in your equation. So we're going to rearrange this equation to make x the subject. So to do that, I'm going to take the cubed root of both sides. So x is going to equal the cubed root of y, And this bit here is my f of y. It's my function in terms, function in terms of y. That's the bit I'm going to put in my integral. So cubed root of y goes there. And the way I'm going to set this up is I'm going to say, well, this bit here is going to give me a negative integral. So I'm going to calculate that bit first. And when I do my antiderivative of all that and I substitute all the right upper and lower limits into that, I get this thing here, which is negative. Makes sense. It's to the left of the y-axis. And then work out the definite integral between 0 and 5 of my f of y function, delta y, or dy. And you get this as a definite answer, okay? So when I anti-differentiate that and substitute in the right limits, this is what I get. And now what we're going to do is we're going to convert any of these negative sections, any of these negative parts, into positive areas. And all we just need to do is make this thing positive, add them together, and we are done. Okay, so you end up getting 9.66 if we round to 2 decimal places, or this would be, I guess, the exact value of combining the two areas together, the two regions. But just like before, we can do the same thing on our calculators using the absolute value function. So if we put the absolute value function in there, so just show the screen grab of the calculator here, between -3 and 5 on the y-axis, we end up getting 9.66 for our function. One final thing I will say in our video is sometimes with these questions, it's quite common that they will say the x values at these points, and what you need to do in order to get the right integral value, the right upper and lower limits, is you need to substitute the x values into your function to get the correct y values for the thing. So they might have a graph, like a graph like this, and they won't tell you the y values straight away that you want to integrate between. They're going to say, find the area of this region trapped between the curve and the y-axis, but they'll give you some x values. They might give you the x value at the 2 points that are really important. And so what you need to do is substitute those x values back into your equation, back into your rule. So back into, in this instance, it would be, sorry about zooming out and in here, into this thing here, and get your y values for the lower and upper bounds, and then use them in your definite integral. Because if you don't use these y values, if you use x values in this definite integral with this stuff over here, it's not going to make any sense whatsoever. It's not going to work. Okay, so you must, these values, if you're doing the area trapped between the curve and the y-axis, must be all in terms of y. So everything y is in here. Y. The reason why it doesn't work is if this was x and you did the antiderivative of your function and you're substituting in these values into your antiderivative, there's not going to be any x's in your antiderivative. It's just going to have y's in it. So that's why it's not going to work. Okay, so that is going to be it for our live stream today. And as I said, tomorrow is going to be where we look at exercise, actually not tomorrow, on Thursday I will do exercise 9.3 and 9.4. And if you don't have methods on Thursday, that's okay too, because these videos will get uploaded to YouTube and you can watch this anytime between now and the next time I stream. Okay, so that's all for now. Have a safe and happy holidays in case I don't see you again.